Okay, so last time, so let me just say for the recording's purpose, I just started the recording right now. Um, we're going to be focusing on reading part 2 of Wingard over the next 2 weeks. So that will be the reading and also the homework assignment that'll be due. So we postponed today's homework assignment till Monday. You can thank Akash for requesting that, which I think was a very good idea. But we can still answer some. I don't have too many new slides to show today, so we'll have time to discuss questions you have on the homework at the end today. When we and then we can discuss the homework a little bit more on Monday as well. So the next homework will focus on maybe a few more problems from Thorpe, but I think most of the good ones are already taken for this week's homework. And then the next one will be Wingard. Those questions drawn from part 2, or maybe supporting questions drawn from part 1 that are on the same topic. That'll be the plan. But today we're going to wrap up the end of our discussion of the ocean boundary layer. And for those of you who have seen, who have looked a little bit ahead to check out what's in Wingard, you'll see that Wingard is a lot more mathematical and detailed than Thorpe. So in a sense, what we're doing now is we're looking at the pieces that will be phenomenology for what we see in more mathematical detail when we think about the atmospheric boundary layer. And broadly, partly because meteorology is more of a direct impact on our lives, and partly because air is transparent where seawater is not, we know a lot more about the atmospheric boundary layer than we know about the ocean boundary layer. I guess we also live in the atmospheric boundary layer, so it's our home. So we know a lot about it because that's where we live. So we don't, while we may visit the ocean boundary layer, which makes it unlike the deep ocean, we don't stay there very long typically. So we will take the pieces of discussion that we've thought about from the ocean boundary layer, and we'll see how they are reflected in a more mathematical sense when we switch over to the atmospheric boundary layer for the next 2 weeks. Then we'll come back to talk about the linkages between 3D turbulence, which has really been the focus of both of these boundary layer discussions, and the 2D and quasi-geostrophic turbulence as we start to think about the oceanic parameterizations. We're going to talk in detail about the ocean parameterizations of mesoscale eddies, submesoscale eddies, boundary layers, and some of the atmospheric pieces as well. But in the atmosphere, the mesoscale of the atmospheric synoptic scale, which is the dynamical equivalent of the ocean mesoscale, has just normally been resolved in weather models and climate models rather than parametrized. And the atmospheric submesoscale, which is the equivalent of the ocean mesoscale, the atmospheric, I've gotten myself tangled. All right, so one of the problems is that mesoscale and submesoscale are frequently used based on a dimensional length scale, like 100 kilometers is the mesoscale in both the atmosphere and the ocean. But the ocean mesoscale has the dynamics, that is quasi-geostrophic dynamics, that resembles the atmospheric synoptic scale, which is on about 1,000 kilometer scale. So there's a funny nomenclature issue. Hopefully we won't get tangled up in this. We're trying to be dynamical in approach, so we're thinking about things where quasi-geostrophy is important. That's either synoptic in the atmosphere, mesoscale in the ocean, things where the hydrostatic Boussinesq equations are important. That'll be the atmospheric mesoscale or the oceanic submesoscale, and things where 3D turbulence is important. That'll be the atmospheric submesoscale and boundary layer scale and the ocean boundary layer scale. So hopefully that's sort of clear. We'll continue focusing on that for the remainder of the class. Okay. Last time we dropped off, closing out after we talked about a bunch of different ways to measure the ocean, starting our discussion of how the turbulent fluxes and the dissipation rates of both energy and tracer variance. And so we're going to continue that thread. And let me just rewind a little bit back to what we meant by fluxes and what we meant by the dissipation rates and how we might measure those things using the covariances of various fields. So the slide I'm showing right now has the temperature transport, which is like a Reynolds stress, and then it's a covariance of two different quantities, but it is a velocity and a temperature together. We could have also done velocity and salinity together and come up with a salinity transport, turbulent transport, I guess I should specify. Or sometimes we might approximate that with an eddy diffusivity, which would have the mean gradient, the gradient of the mean field, the dt bar dz, and some diffusivity. Or we could think of the kappa here as being the real molecular diffusivity, and then the Reynolds stress, or this covariance between the velocity and the temperature, as being the turbulent part. In that case, we could take the ratio of the two and think about it as indicating how turbulent the flow was versus how diffusive it was. Those kind of ratios of molecular or viscous or diffusive fluxes to turbulent fluxes is sometimes, there's another dimensionless number, which is the ratio of those two, called the Nusselt, Nusselt number, which is kind of a useful thing to keep in mind along with all of our other dimensionless numbers we're keeping track of. But of course, temperature is not actually the thing that's conserved. It's the first law of thermodynamics, so it's the heat that's the conserved quantity, or perhaps the entropy if you're thinking of potential temperature. But in either case, we might want to convert using our fluxes of temperature into something else like fluxes of energy. So the energy or heat flux is really, in the Boussinesq system, just has the background density, rho zero, the specific heat capacity multiplied by that same temperature flux. And since the specific heat capacity and the background density don't vary at leading order in the Boussinesq equations, it's just a change of units. There are constants, or effectively constants, that you can multiply that same temperature flux from. So if you had very deep convection, you might worry about the fact that the background density was changing, or even the specific heat capacity was changing. And so you might have triple products of this, and that would be true in the atmosphere when you had, so the troposphere has a pretty decent pressure variation across it and density variation. You might worry about that piece, but since we're focusing on boundary layers in the atmosphere and the ocean, as we're thinking about turbulence, we can safely keep that rho zero equal to a constant and Cp equal to a constant, which is essentially the range of depths over which the potential temperature isn't that different from the temperature, or the range of elevations in the atmosphere. Okay, so temperature flux, heat flux. Okay, when we get to velocity, we think about it as being a stress rather than a flux, or that's the same word for almost the same concept, except the thing that's being transported is a vector rather than a scalar. So when we have a viscous stress, it's kind of, the tensor complexity is kind of suppressed because the viscosity is often approximated to be isotropic, or a scalar viscosity, which means that the gradient, the flux, momentum and gradients is a simpler tensor operation. But when we think about it in terms of the Reynolds stress, we see that we have both, it's the covariance of two different vectors. So equivalently, a second rank tensor. And so we're going to have a bunch of tensor stuff coming soon. This is the vertical transport of the horizontal momentum in the x direction written here, but we'll see, we're going to have to crank up our tensors in a little bit. And then the one last piece that's an important flux to think about is the buoyancy production, and that's a really important term because it is the key way that the potential energy budget communicates with the kinetic energy budget. This is, we talked about it last time, this is if WB B on average is positive, that means that buoyant stuff is going upward and dense stuff is going downward, which means that potential energy is being extracted from and converted into kinetic energy. Or on the other hand, if you're doing mixing, then warm or light stuff is being pushed downward and dense stuff is being lifted upward. And so buoyancy production or buoyancy flux in the same direction as gravity, WB on average, is the conversion between potential and kinetic energy. So we're going to see that's really important. It's complicated to measure these things. We won't dwell on that any more than we did yesterday. So the other covariance or complicated products that we might want to be interested in is the dissipation of energy. So this is epsilon, remember, is the dissipation of kinetic energy. Eta, we've talked about it as being the dissipation of entropy or potential entropy. That could also be measured with a similar kind of tensor formula. And then there's also a chi, which is the dissipation of tracer variance. So in an anisotropic flow, at the viscous with the real viscosity, this is what the dissipation rate is. It's the strain rate squared. And since the strain rate is a tensor operator, a symmetrized velocity gradient, so du in the I direction by dx in the j direction plus the one with j and I swapped, that's symmetric in I and j. And then if we use Einstein's summation, that is repeating over all the values I could take, x, y, z, repeating over all the values that j could take, x, y, z, summing up all of those pieces, that's what this object is. Epsilon is a scalar, which is the double contraction on both directions, the I direction and the j direction, of this strain rate product. But in an isotropic flow, if you count up how many of these there are, there's a factor of 15 that's coming from the different sums that are embedded in there, and then you really only need to measure one gradient. Yes, Akash, good question. The angle bracket here does denote averaging. I was using the same notation for averaging that was in Thorpe, where he uses the angle brackets. Wingard uses the overbar, and Vallis uses the overbar most of the time. So from our perspective, angle brackets and overbar are not really distinct. I don't think we've made any real distinctions between the meaning of either one of those. Good question. Thanks, Akash. So back to isotropy. So isotropy in the isotropic limit, where then we could just estimate this from any old velocity gradient we happen to have, any old, perpendicular, take the derivative of one of these velocities in a different direction. And the most convenient one to do is the horizontal velocity component in the vertical direction when you're in a boundary layer. That's something that's pretty easy to measure by just letting that microprobe fall through it. Here it is. Then you get an estimate of epsilon under the assumption of isotropy that goes like this. Okay. Similarly, temperature variance could be estimated if you had all three derivatives of temperature like this, or if under the same kind of assumption of isotropy, you could simplify that down, and then under isotropy, each of those gradients would be equal to each other. So in this case, it's pretty easy to see that this is just a factor of 3. If this equals this equals this, it would be 3 times any one of them. So here's the most convenient one, the dt dz. And there's the microstructure profiler that might fall in that. And then we talked a little bit about a lot of these different statistical quantities we can have to explore what's going on inside those covariances and stuff. We'll come back to those as we go. And then we talked a little bit about Hijinx paper quantifying the contributions to stationary homogeneity and isotropy in one particular example. This is kind of a nice conceptual framing to keep in mind. When we're assuming these things are true, we're basically losing the error bars here, but maybe that level of error bar isn't so something you have to worry too much about. And in the boundary layer case, where assuming that we're safely within all these three conditions holding, so long as we have the right kind of averaging. So you might say a 10-minute average or a 20-minute average of all the flow statistics would be relatively isotropic, homogeneous, and stationary, on at least on small scales. Okay. All right, so are there any questions about those pieces from the review, or should we move on to thinking about the turbulent energy cascade, or turbulent energy balance? Okay, the turbulent energy balance. So one of the reasons why we might like to know all of those pieces is because, just like we saw in Vallis when we thought about the energy budget, we could estimate an energy budget for the turbulence. And this is the simplest form of that you might see, that Thorpe puts out in words. But we actually are going to see in Wingard, we're going to see how to write all of these different terms in this budget and how to derive this budget from scratch. So that will be part of the things we cover at the beginning of next week. We'll go through the derivation of this equation from scratch. But even before we see how it's derived, I think it's useful to kind of get a conceptual hold on what it means. And you'll see that those fluxes and those quantities we were just talking about come back into this energy balance in a way that's going to be helpful. So measuring those things allows us to close the budget for energy, is the idea. Okay, so we're talking about the turbulent energy, or sometimes the turbulence energy. It's the energy of the turbulence, and so both of those are equivalent languages. Or sometimes it's called the TKE budget, the turbulent kinetic energy budget. Or you could also think about a TPE budget, the turbulent potential energy budget, but usually it's the turbulent kinetic energy and the mean kinetic energy and the mean potential energy that we're thinking about. It's a little bit less common to think about the turbulent potential energy, at least for 3D turbulence, but we'll see when we get to quasi-geostrophic turbulence, the turbulent potential energy, or the eddy potential energy is what it's usually called, is an important part of that budget. So, okay. So, what it controls the rate of change of turbulent kinetic energy in a flow. Well, we have things that can produce turbulent kinetic energy. And so, rate of production in this sense is really the production by the mean flow. So that's a conversion of kinetic energy from the mean flow kinetic energy into the turbulent kinetic energy. That's what this first term in this budget is thinking about. The buoyancy flux, as written here with a plus sign in front of W prime B prime, that is exactly what we just talked about. That's when we convert potential energy by letting light stuff go upward and dense stuff go downward. That produces turbulent kinetic energy. That's the second term in this budget. And then the third term in this budget is the rate of dissipation of kinetic energy, turbulent kinetic energy, which is exactly that epsilon we just calculated, which is the strain rate squared, or strain rate double contracted. Okay, so the only unfamiliar term here maybe is this rate of production by the mean flow. So let's look at that one for a second. So written out here in the generic form, it's the Reynolds stress, UI, Uj, with the rho naught out front. So this is the Boussinesq form with the rho naught separated from the UI, Uj. And then look, it's contracted into a mean, and here I'm following Thorpe's notation, which is a large U for the background flow, the large scale flow, and a small u for the turbulent flow, rather than a bar and a prime. But you could also think of this big U as being a U bar and the little u as being a U prime. Primes sometimes are written with lowercase, bars sometimes written with uppercase, angle brackets are sometimes denoting an average, over bars are sometimes denoting an average. So those are kind of equivalent notation. We're switching back and forth. between, as we switch between Thorpe and Wingard and Vallis. Okay, anyway, so that's what this thing is. So let's think about how it contracts. So this U and this U are dotted into different parts of this mean velocity gradient out here. This thing is obviously symmetric because U is no different from U, so we could switch the I and the J and would make this thing symmetric, but this thing is not symmetric. This is the gradient of the mean velocity, so it's the mean velocity in the I direction taken partial derivative in the J direction. So this thing is not symmetric. So if we had a flow that was along the surface of the ocean, we might have a U, in the x direction that was non-zero, but it might not have any gradients in the x direction, but it would have a gradient in the z direction, so in the vertical. So that's the kind of thing you might think about it for this side. Now, which Reynolds stress would produce kinetic energy from that? Well, if we took the fast-moving stuff near the surface and moved it downward, and took the slow-moving stuff at depth and brought it upward, what kind of a Reynolds stress would do that relocation? That would be if we had one of these U's in the same direction as the flow. So if the I direction was in the x direction, and then the other one is the same direction as the gradient. So if the J direction was the Z direction. So if we had U, W, D, big U, DZ being a positive number, that Reynolds stress would be homogenizing, smearing out the energy by reducing the mean kinetic energy. So I hope that makes sense to everyone. Are there any questions on that? Okay, great. So we talked about this same process when we talked about redistributing the shear flow when we were discussing Vallis. And actually, remember the day that we talked about increasing the separation distance with the tables in the classroom versus and how that worked out, because area has a different power than circumference. And we related that to the idea that momentum has a different power than energy. So even while conserving momentum, we could redistribute and gain energy. That's exactly what this term is talking about. It's the redistribution, conserving momentum, that allows us to convert mean kinetic energy into turbulent kinetic energy. Okay, so this is one of the energy balances we're interested in, the turbulent energy balance. And of course, we could have a mean kinetic energy budget as well, which, if assuming the dissipation is all happening at small scales, that wouldn't affect the mean energy budget at all. The buoyancy flux, it would be, you could have a large scale buoyancy flux, like maybe in the atmosphere, the pole to equator temperature difference working against that would be producing large scale atmospheric kinetic energy. And then the rate of production by the mean flow, this shear production term that's producing TKE would actually be a sink in the mean flow kinetic energy budget. So this is a transfer term from the mean kinetic energy to the turbulent kinetic energy. And now if we start thinking about the buoyant energy the buoyancy production is actually a transfer term from the large scale potential energy into the turbulent potential energy. That's the next budget we want to think about. So how does that work? So if we have some stably stratified density profile, so schematically shown here from the figure from Thorpe, this stuff up here is less dense than this stuff down here. But if we imagine there was a turbulent overturn, we might end up with a density structure afterwards that looks a little bit like this one, this part C1, where the light stuff up here is still up there, the dense stuff down here is still down there, but this overturn has mixed up some of the density surfaces. So put light stuff on top of dense stuff, and then there'd be all kinds of turbulent overturns and things. Or if we think of it in terms of a buoyancy over here, or anomaly displacements of density. Oh, sorry, this is a length scale that, sorry, let me come back to this length scale over here. Here we would have this one would be anomalously dense. This is anomalously light, anomalously dense. So we'd have a B prime that was negative here, positive here, negative here, positive here. There's some B prime implied with that. Well, where does the B prime come from? Well, it comes from the vertical displacements in the presence of this background density field. How far did we have to displace a fluid parcel to get this density prime? Well, we could think of it as being this piece of fluid is finding itself anomalously dense because it was displaced upward by a length scale eta. This one is anomalously light because it's representing a hunk of fluid that was displaced downward by a negative value of eta, positive eta, negative eta. Thorpe, one of the reasons why Thorpe is famous for turbulence study, thought if you take this density profile and reorder it, you can estimate how far you have to move all these density anomalies to get back to something that looks like the original density profile. In fact, if all the density was exactly conserved and there was no mixing, just stirring, this density profile, once you ordered it from the lightest to the most dense, would be the same as this original density profile. In fact, in this overturning process, there is some mixing, so we wouldn't expect to get exactly the same density profile, but we'd get something that's pretty similar. So what Thorpe conceptualized was if you figure out how far you have to displace things, to get these displacement distances, how far you have to displace things to get it resorted back into its order from least dense to most dense, the RMS of these displacements is what's called the Thorpe scale. So it's the RMS distance required to adiabatically resort to a stable density profile. And you can imagine, if you did that, you could keep track of how far you're moving those buoyancy anomalies. And if you thought of it as happening in a particular rate of time, you could, we know how long it is between here and here. So that is the potential energy that is being injected by the turbulence, that is converted from turbulent kinetic energy into mean flow potential energy, because this one has more potential energy than this one, or certainly more potential energy than this one, resorted into increasing density with depth. So this B is kind of a rate of either the stirring bit, which is putting the light on top of the dense, and is the part of this, or the unsorting of that, or the resorting back into the stable profile would say how much restratification you would get in what rate of time. So this buoyancy production is really the key to thinking about how the potential energy is either created or destroyed, and the Thorpe scale is giving you a sense of how the distances required in that resorting process. So that's a nice way to think about the potential energy. Okay, so we thought a little bit about kinetic energy, we thought a little bit about potential energy. How might we determine those from a model? So we talked a lot about approximate equations when we were thinking about them in Vallis. This is a form which is similar to what Vallis has. This is actually from one of my papers, but here we're making explicit, this is the underlying equations here. This is a dimensionless form of the full non-hydrostatic Boussinesq equations. But keeping track of all the dimensionless terms, so here's the Rossby number, here's the planetary number for beta, here's the Reynolds number measuring the viscous term to the inertial term, here's the Froude number, which is measuring the stratification, here's the ratio, the aspect ratio, which is the one, remember, that came in to be important in whether we were in the shallow water limit or not. What else we got? This epsilon, sorry, this is not the same as the turbulent epsilon. This is a crazy thing that can, depending on whether The pressure is balanced in geostrophic balance or balanced in a turbulent balance, needs to have two different limits. So this is a rather complicated set of equations. But what we can do is we could derive an energy budget or a potential energy budget or a small scale turbulent kinetic energy budget from this set of equations, or we could derive a QG set of equations from this set of equations and propagate back how the Rossby number or the Reynolds number or the Froude number or the Peclet number appears back in those energy budgets. That kind of process then gives us a handle on what these budgets would look like of either potential energy or the turbulent energy, like rate of production by the mean flow. How do we have a Rossby number in front of that? Do we have a Rossby number squared in front of that? Dissipation rate. We probably got a Reynolds number somewhere in there, maybe a Rossby number 2. We could think about how these different terms, which one is big and which one is small at different scales by evaluating the dimensionless flavor of an energy budget. And now let me introduce one more concept. This asterisk on these dimensionless numbers is really thinking about a model with finite resolution. So what I'm saying here is we take the dimensions based on the model grid. So that might be a DZ vertical model grid or a delta S horizontal model grid. And in that case, then it would be the Froude number at the model grid or the Reynolds number at the model grid. So why am I emphasizing the model grid is because when we switch gears to start thinking about how we model all these systems at limited resolution, the limited resolution is what's going to govern the relevant Reynolds number or the relevant Rossby number, or the relevant Froude number, or the relevant aspect ratio, or the relevant Peclet number for that particular model. And if the Peclet number was really big, the Reynolds number was really big, then all these diffusion terms would be negligible. But we'd still have to figure out how to keep that model under control. And so we might need to inject some turbulent approximation, something like an eddy viscosity or an eddy diffusivity, in order to keep the model in check, which would be a parameterization, an approximation of the turbulent stresses and turbulent fluxes of temperature and salinity. That's the Smagorinsky game we talked about a little. Well, we're going to revisit that after we're comfortable and think about how we do that in the case of boundary layers. Does that make sense to everybody? Okay, let's spend a few minutes talking about the ocean boundary layers, the way they might be forced, the way the different vertical structures we might get, and as we're building toward the atmospheric boundary layer over the next 2 weeks, we're going to see that there's a lot of similarity, at least between the dry atmosphere, that is the atmosphere not including humidity, and the temperature-only ocean, that is the ocean not including salinity. They have essentially the same equations in motion, except the wavy interface, it will have effects through the Stokes drift on the ocean that is not so obvious in the atmosphere. So let's think a little bit about that phenomenology before we quit. There we go. So these are some nice schematic pictures from Thorpe to give you some illustration about what you might think about in an oceanic boundary layer near the bottom of the ocean or near the surface of the ocean. So he's got the wavy surface with little waves, or the bottom with this hatching is the bottom. So we might have a shear layer at the bottom where, the no-slip condition at the very bottom would go to 0. And then up here we might have some geostrophic flow in the interior. And there's turbulence produced by that shear zone. So that would be a shear production-driven system. You also might have hydrothermal vents releasing warm water out of the solid earth into the ocean, or an oil spill releasing buoyant oil particles or buoyant gases like methane. And that would drive a convection-driven bottom boundary layer. But at the surface, we also have a condition like that because we have wind stresses that would blow at the surface. And so you'd expect to have a shear layer between the wind-driven surface and the deeper ocean. And as we know, in the rotating case, if that wind is persistent, we'd expect to have a surface wind-driven Ekman layer or a bottom Ekman layer, because we would keep rotation in that balance that gives us the shear zone. And then so there would be turbulent flow driven by that shear, so against a shear production driven turbulent boundary layer. And that mixing would tend to eliminate all the gradients in density. So there would be a relatively homogeneous density across that mixed layer. This part is driving a mixing process. So we might think of it as a mixing layer where the turbulence is actively mixing. And where it has already mixed the density, we might think of a mixed layer. The mixing layer could be shallower than the mixed layer if the mixing is weaker than it used to be, or if the wind picked up and the mixing got more intense, we might expect the mixing layer to be deeper than the mixed layer for a while it was digging down and entraining into the pycnocline, this region of increasing density below the mixed layer. Instead of wind, we could have done it by cooling at the surface, which would have made, these are warm plumes coming upwards. Cold plumes going downward would have been another way to mix our mixed layer. So we need to think both about the shear-driven turbulence, where the turbulent kinetic energy is created from the mean shear in either a wind-driven or a bottom shear profile, and the convective case, which is either heating from below or cooling from above, which gives you buoyancy production that's driving an injection of potential energy through buoyancy-driven turbulence. We could have an intermediate layer that isn't a boundary layer, but it's a layer between two different layers within the ocean at the base of the thermocline, the base of the pycnocline versus the ocean abyssal interior, kind of the bottom of the gyres. This tends to happen. This also happens in the atmosphere at an inversion. A capping layer can have this kind of a flow pattern. Or you could have waves, internal waves, like we talked about last time, overturning and driving a little bit of intermittent braking somewhere within the interior of a stratified fluid. That's what this one is showing. You could have waves, lee waves, generated behind a bump on the bottom of the topography, generating an isolated lee wave mixing problem. Or you could have, this is a kind of funny schematic, something called double diffusion, which is when you have a temperature and salinity structure such that the density was stable, but actually because temperature diffuses faster than salinity, you can still get an instability that occurs due to small scale fingers which are moving. This is when you have warm salty water over fresh cold water. Then you might have that kind of a mixing process. This is a sort of an interesting aspect of the ocean dynamics of temperature and salinity. You put all this together, you get a very complicated set of mixing processes. Is C evaporation? No, C is not evaporation. This is more an injection from hydrothermal vents in the ocean case. So this is warm water being heated by kind of volcanoes on the bottom of the ocean, if you like, or other escape of geothermal heat into the ocean profile. Evaporation, if we evaporated the surface in this B, that would tend, if you evaporate, so you remove the warmest of the warm water and make it into steam, it actually tends to leave cold water behind. So there's a latent heat flux implied by that, and that would tend to drive cooling convection. That's case B here. All right. So in convection, we might think that we have a buoyant production of energy, which might be approximately in balance with the dissipation. So if we go back to our total energy equation, after a while we might neglect the DDT term, and then we might think of there being a balance between either buoyant production or mean flow shear production, balancing dissipation. And so in the convection case, that's the balance between a turbulent dissipation and a buoyant production. So that could happen either from warming from below or cooling from above. And we could think about how to estimate those two different terms and think about that TKE balance. In stress without convection, we would have the stress. So here's the shear production. This is these units are a little funny. I probably shouldn't have a row knot there. Anyway, this is one of the stress-driven layer. So we could have a shear stress of production balanced by the dissipation. In this case, you can actually go through the math and away from the wall where you're not in the roughness part where you might have roughness contributions, and away from the interior flow where you might have shear from some other region, you actually get something called the law of the wall or the log layer, where as a function of the log of the distance, the mean flow goes exponentially. There's a relationship between the log of the distance and the mean flow. So there's a prescribed shear that's consistent with this production dissipation balance. Thorpe goes through this in detail, but basically the idea is you estimate what the stress is using the friction velocity, which is actually just a relabeling of the stress in the units of velocity, like this. This says that the only way you can get a mean shear, and the only thing you can make that's made out of U star and Z, that is Z being the distance from the boundary, has this units with a particular constant, a dimensionless constant called the von Karman constant. If you make this assumption and then you integrate this equation, so this has a derivative in Z, this is 1 over Z, so you get that kind of a solution. So it says that the mean flow shear, or the mean flow as a function of Z, should go logarithmically with Z across this layer. It's called the law of the wall or the log layer. Closer to the wall, you might have a roughness length that, with bumps, either a canvas of trees in the atmosphere or bumps in the bottom of the ocean. But in an intermediate range, you could think about estimating what this friction velocity is, i.e. estimating what the stress is at the surface by comparing two different depths, Z1 and Z2, both within the log layer. You could work backwards and see what the stress was at the surface. So this is a good way to measure the stress in one of these shear layers without convection. And you can also estimate the epsilon this way. By figuring out U star this way and then plugging into this formula, you could estimate what U star cubed over kappa Z was, which is a good estimate of the dissipation rate. If we put convection together with stress generation, we get something called the Moana-Nabokov scaling. The Moana-Nabokov scale is a length scale that comes out of thinking both about the wind stress and the strength of buoyancy forcing at the same time. Turns out the only way to get a length scale out of those things is like this. Well, not quite the only way. There's a von Karman constant sitting in here, which is done for convenience to make sure that you get back to this kind of log layer with a K in the right place when you're in the Moana-Nabokov limit. But here it is. So it goes like U star, the friction velocity cubed, over K times the buoyancy flux, and has this funny minus sign because, interestingly, this is a length scale that can be positive or negative. When the length scale is negative, we take that to imply that the boundary layer will be unstable. And when the length scale is positive, that's when the boundary layer is stable. When the buoyancy flux is neutral, that is just a shear only layer. That's not a stress and buoyancy forced layer. So this is our insight, starting to think about, we're going to spend a lot more time talking about this in the boundary layer of the atmosphere and whether this varies as a function of Z, etc. So we're going to come back to the Moana-Nabokov detail over the next couple of weeks, but I wanted to give you the idea that what it's talking about is it's talking about things that are forced both by the wind and also heating or cooling at night, heating during the day with the sun, cooling at night. So you might have an unstable layer, which is a shear layer in the presence of convection, or a stable layer, which is a shear layer in the presence of restratification by the sun. And somewhere in the middle of the afternoon, in the middle of the morning, you might have an in neutral case in between. And we're going to see that when we think about this, we're going to start seeing that there are different layers within the boundary layer that might be dominated by shear or dominated by convection. And this is just two examples showing us that when the z over this Moana Nabokov length is less than 1, we tend to see a mixed layer. And when it is greater than 1, we tend to see a drop off of the turbulent dissipation. So this is a layer measured in terms of the dissipation as scaled by the buoyancy flux. So this is saying there's a lot of turbulence doing a lot of dissipation here within this boundary layer where z over that Moana Nabokov length is less than 1, closer to the surface than 1. In both the ocean and atmosphere, they have the same characteristic. We're going to come to understand that a little better. So the last thing that I wanted to talk about is the surface waves, and we already hinted at that a little bit. You know, these big waves all over the ocean surface. And one thing that they do is they make the Lagrangian fluid displacement, that is, following a hunk of fluid, it moves faster within the waves than it does below. This is called the Stokes drift, the average of the wave field over this phenomenon, as the waves pass by. And if you go through the details of trying to average out the governing equations, including this Stokes drift, you find that just like Reynolds stresses affect the governing averaged equations, the Stokes drift also affects the governing equations. So we're going to come back to this and talk in detail about how this affects the turbulence in the upper ocean. We'll actually probably go through Nobu's paper in detail that's listed here, where we think about some of the effects on turbulence. Okay, so let's stop there. Are there any quick questions on the homework while we paused here? We can talk more about the homework on Monday too, but let me open up the homework now. So, there was one question about the final project proposal abstract. You can just include that as the last page of your homework. That's the easiest way to do it, and I will give you feedback from there. Some of you have already emailed me questions about aspects of that. Please feel free to get feedback before the official feedback if you want. It is totally fine for this final project to relate to other papers or other projects you might be working on. That is your thesis, your prelims proposal, your paper that's in draft right now. The only thing that we ask is that it should be consistent with the notes. So that means that it needs to still be a review paper, and that involves at least 2 papers from the literature. Now, if you're writing the intro to your thesis, you might take the intro to your thesis as the guiding principle for what your final project paper is going to be, because that is certainly a review paper that involves more than one paper. If you are writing your prelims proposal, you can certainly have a version of your prelims proposal that covers the literature review part of your prelims proposal. All of that is supposed to be fine and is definitely within the bounds of the kind of project we're doing here. The idea is just to bring turbulence into this review paper, and turbulence and submesoscales and QG and all that stuff into your research project outside of the class. Have the homework due on Monday instead of today. Oops. Valist. Oh, yeah, good question. So this is an integral with wave number of a time scale. And then he's coming out with a time here at the largest scales. Yes. If this has units of time and this has units of time, and this has units of wave number, no, the dimension is not correct. So this should be the integral of time scale divided by the difference in the bounds from top to bottom. As this goes to infinity, that's a little bit tricky to figure out. Because then both the numerator and the denominator will depend on k. So you will have to do some cancellation between the results of this integral and the averaging scale over which it is integrated. Any other questions on the homework that have come up so far?
Yes, I have a question.
Sure.
About exercise 3, the same.
Yeah?
When we have to compute to solve the last point about the atmosphere,
Mm-hmm.
and do we need to know the epsilon or eta values?
No. You could convert to epsilon and eta values that were specific, but I think what he's suggesting is that you just consider the Kraichnen approximation where you have a k to the minus 3 connected to a k to the minus 5/3 at a different scale, and it be careful which one is the large scale and which one is the small scale. It will be backwards from Kraichnen for the atmosphere. That is, k to the minus 5/3 will appear at small scales. K to the minus 3 will appear at large scales, backwards from what Kraichnen implies, because there's a large scale entropy cascade and a small scale 3D turbulence cascade superimposed. But if you just assume that shape for an E of k with a constant that is not specified versus epsilons and etas, but just assume you've got that kind of a shape and that it's continuous so that it meets at a branch point, you should be able to set up an integral where you can estimate that scale all the way down to with any bounds on the limit. So basically, he's encouraging you to take a piecewise linear scaling for tau sub k, rather than a single inertial range scaling over all scales, the way the first part of the question works.
I also have a doubt in question 3. It's kind of stupid, but so they talk about Ks and Kl, and Ks is small scale, so that means Ks is larger than Kl, right?
Yes. So be careful about the signs. He has large scale, so he's going from infinity up to 0. You might want to flip the sign on that. I think just like he has the dimensions wrong, I think he also has put those backwards. So
Small scale Ks means small length scale, not the small wave number scale or something like that, right?
yeah, well, you should be more clear than Vallis is. Vallis has clearly done this in a casual way. I would have preferred he'd say that it was a small k on the bottom and a large k on the top. But the time scale should be positive definite. So flip them if you want the small wave number on the bottom and the large wave number on the top, so that you get a positive definite thing, because tau is positive definite as well.
Okay.
And sorry, there was one more question from Ming-Chi in the chat box. Let me go see if I can find that. Thor change the figure 2.6 is for the velocity squared, while we're asked to go to the scale estimate of the vertical velocity. Oh, how can we derive the constant we need from figure 2.6? Take the square root. Use the RMS vertical velocity. So estimate the velocity squared, which is sometimes called the vertical kinetic energy, and then take the square root of it after you pull it off of that figure. in general, it's very happy and convenient often to take the square root of an energy and call it an RMS velocity scale. That's something that people do in turbulence all the time, so much so that people forget that that's actually a pretty specific model for how the velocity scales in turbulence. And as we know, I can't bring it back up easily, the PDF of turbulence is actually not very Gaussian at large velocities and small velocities, or large negatives and large positives. It actually goes towards an exponential tail. So you might get worried about whether the TKE, the square root of that, was actually a good estimator of the larger intermittent velocities. That's a detail that is of interest, but maybe don't get worried about doing it that way for now. Okay, any other questions, or should we close? All right, so feel free to send me email questions if you have more questions about the homework over the weekend, and we'll see you on Monday. We'll have a wrap up on the homework questions that are still lingering after everything gets turned in on Monday as well. See you all on Monday. Have a happy and safe weekend.